what is a classification? Okay, so what does it mean, classification? Now, classification means that, you know, I have a vector that is n dimension. The vector is, this vector is measuring, so it's model, as depends on a limited set of the classes. Now, this set of classes, okay, which I indicate as k classes, this set of classes, you know, is what we want to estimate. So we want to define this specific vector to which classes this vector depends. No, so you know we need to decide essentially to which class is each individual vector is depending. Now I can, you know, you have seen something on the workshop, and I can make more examples. And you know, the most straightforward are recognize the handwriting. You have the letters. You want to recognize the handwriting. So to recognize the handwriting, our classes are the letters. So A, B, C, D, and so on. Okay. You have a handwriting, so you write by hand A, B, C, and you need to recognize which class is the set of, for instance, pixels that are representing a letter. So I have the letter A, you know, have a certain number of pixels, and so these number of pixels are, you know, are belonging to a specific class. Now, the size of X is important. So the vector X is important because the vector X is, the size is the data in it. So now you just to figure out, so imagine that, you know, I have a letter A. Now this letter A, if you imagine that we use a pixel, okay, to represent the letter A. Okay. Then this is the handwriting. So, and this is the set of samples that in the image are representing the letter A. So then I take all these samples in order. 1, 2, 3, 4, 5, blah, blah, blah. Then it is, you know, 10, 11, 12, 13, blah, blah, blah. And then until I have n. Okay? So these n samples, you know, it could be the n samples related to this set of pixels that are representing the handwriting letter A. Then I have a similar with B. So let's call this one as the class H1. Then I make a B, which is the class is number 2, and so on. Okay? So when I take a pixel, a set of pixels, which is, I don't know, it's representing something, I need to find these set of pixels that are X, which are the size n, which class this one belongs to. Okay? So what class? Now, once that I understand the class, I understand the letter. Okay? So then, you know, I can make the handwriting, I can make faces. Well, you know, I have a set of faces. I can make features. I can make features of the faces. Okay, this way. So I can arrange different way. Now I can make a signal. I can make a radar. Now in radar, I mean, in early day, in signal processing, the detection theory started from radar. And from radar because, you know, the goal was to understand if there was a target or not, if there is an enemy or not. Okay. So now we are, and by the way, if there is enemy 1, enemy 2, enemy 3, friends or nothing. You see? So these are different classes. Okay. Now, so given that, you know, we can find as a way to understand how we classify that, we can use, for instance, the maximum likelihood classification. So, what is the maximum likelihood classification? Assume that I know the probabilistic mapping between class and data. So now you know the maximum likelihood is the maximum likelihood classification is that given x, which means given that one, okay, I can calculate the likelihood of each of that class, which means I can calculate the probability of that data with respect to H1, the probability of X with respect to H2, and so on. Now, you know, if you want, loosely speaking, it is like if we want to estimate the specific shape where our set of parameters is countable. In other words, it means that you remember, you know, we started saying that I have my model. You know, my model is x equal h theta plus w. And then I said, okay, this is my measurement. And, you know, they have some impairment. My goal is to estimate theta. Now imagine that theta is only, so theta belongs to a limited set, which is theta 1, theta 2, theta k. Okay? So there is just a combination of possible theta. Then I need to decide which combination is the one that describes at best that specific measurement, which is x. Okay? That is the maximum likelihood. Now, in addition, you know, in some cases the probability px hk is not known, and we need to estimate from some training. So we need to get some training to estimate the distribution of px. And in case we do by training, this is called supervised learning. Okay? Yeah, this is what I was saying. Now, so assume that I can do that, and I can write a maximum likelihood. But you know, if I know some a priori, I can do the Bayesian similarly. So what is the Bayesian method? Now the Bayesian method, by bias, you know, I can calculate the probability of the class given the data. So that means that I calculate by the probability of the data given the class times the a priori probability of the class. So in the Bayesian method, I introduce, okay, the information, a priori information about the probability of each individual class. Now this means that the different classes have a different probability. And so depending on the a priori probability of each individual class, then I can calculate the a posteriori probability, and then decide for the class that has the highest a posteriori probability. Put in another way, I can decide the parameter that has the maximum a posteriori probability. Okay? So putting this way, I try to make a parallelism about that. Now, what are the methods? If you remember, you know, when we started with estimation theory, we said, what are the criteria? What are the metrics? Now, the metric that I can use is there are two major metrics. One is the probability that x is equal, so belongs to the class hk, given that it is hk. Now, in that case, you know, that means the probability that this is A, given that it is A. So we can measure as a criteria the probability that I can make a correct classification. So I classify, okay, these, you know, these data, these measurement, these vector x, as correctly classified. On the other hand, I can calculate the probability that x is h high, which belongs to the class high, given that it was generated as a class hk. Now in this case, you know, we are wrong, because our classification is wrong. Now, that means I know that I wrote a letter A. I want to calculate what is the probability that I detect B, I detect C, I classify as B, as C, as D, and so on. Okay, so, and by the way, yes, where's the rule? When the classification involves signal, it's called the detection theory. Okay, so detection theory is, is started from the radar, but I mean, now it's mixed up, okay, and with this intelligent system, it works. Now, let's look at the binary detection theory. Now, the binary detection theory means that I have two possible classes, okay, or two hypotheses, two possible hypotheses that are alternative one another. So I have one or the other. Now, I need to decide with respect to H0 or H1. Now, H0 is called the null hypothesis, and H1 is called alternative hypothesis. Okay? Now, it depends on problem by problem. I can assign to H0, like the case where there is no signal, and H1 there is a signal. This is typical in radar, and that's why it comes to be H0 and H1. H0 means that there is no echo, no radar echo, and the H1 that there is an echo. Okay? And some of the jargon that comes from the radar example. So, one possible way to decide between two possible classes or two alternative classes is that I use the decision region. What is a decision region? Now, look at these examples. I have n points. So that means that my data is x, correct? And this x has a size of n times 1. But the vector n times 1 describes a space that is n-dimensional. Then I can use the decision by mapping into regions. So what does it mean, regions? Now you need to imagine that when I write the letter A in whatever flavor, like here, this letter A and so on, okay? Then the letter A belongs to a particular region, which is the region for the letter A. And the letter B belongs to another region. So now, if I have a multiple classification, it is more complex to see. So with binary, it is simpler. So then, imagine that we have a vector x, and then, we imagine that our space, our n-dimensional space. Now, n-dimensional is too complex, so let me put the special case that n is equal to 2. Okay? So n equal 2 means that, my vector is x1 and x2. But then, this is general for any dimension. So the decision region says that if I stay in this region, then I decide for H0. Then if I stay outside of that, then I decide for H1. So it means that if I have one measurement, if this measurement goes here, then I decide for H0. And if the measurement it stays here, then I decide for H1. So this is for the decision. Then I call this region, this entire region, so the entire set is the one that I call R0. So when a point, which is the measurement, goes inside of the region R0, then I decide for H0. When a value stays inside in the region R1, then I decide for H1. Okay? So these are the two regions. Now, look at that. So imagine that, if X belongs to the region 1, I decide for H1. If X belongs to the region 0, I decide for H0. Now imagine that I generate my model according to the two hypotheses, which is H1 and H0 and H1. Okay? So the column of this table is describing the two hypotheses, and the row is describing the decision that I made. So now, imagine that I generate, so my true value, my true hypothesis is H1. Now, if the vector is the point is belonging to the region R1, then the decision is true. Okay? So then the probability, okay, I indicate with this shorter to say, the probability that a specific point, let me write here, it's only because, you know, so this one says the probability that X belongs to R1 given that you know it was generated as H1. Okay. So this probability is the probability that you know I put the decision in H1 when it was really H1. Then this one is the detection probability, the true positive, okay, probability. Now, so the true positive probability is the detection probability. Detection comes from the jargon, the radar jargon. And the statisticians call sensitivity. Okay? So, probability H1 given H1, which is the probability that I make the true decision given that it was H1, is a certain probability value. Now, if I decide in H1, but the model was generated from H0, then you know I make what is called a false alarm. Why false alarm? Because you know it comes from the radar jargon. Assume that you know I have no echo, I have no enemy, and they decide that there is an enemy. Then you know I make a false alarm. So I have all the people I'm waking up and say, oh here, okay. Imagine that you know false alarm similar is you know you are checking for a tumor. You go to the doctor. And the doctor has a device, and the device is checking for potential tumor. And now, if the doctor says you have a tumor, but in practice you have no tumor, then this is false alarm. Okay, and then you start getting anxious and so on. So false alarm is bad, and you know, and the detection is good because I mean detecting is better not to have the tumor, but you know, so it's detecting the tumor when it exists. Okay. And for instance, I decide to be in I decide for R0. Now, if I decide for R0, okay, which means there is, you know, there is nothing, okay, there is no tumor, you say. But on the other hand, in truth, there was a tumor, then you are missing. Missing means that you are missing the presence of a tumor, okay, which, you know, I'm moving from the example radar, which is far away from for some of you, to some that is more intuitive, which is, you know, is medical stuff. Okay, and on the other hand, you know, missing is bad. Okay, because if you miss, you know, it's bad. Okay, and on the other hand, if you decide that you know, you are healthy and you are really healthy, that's perfect. Okay, and so mixing up that, knowing that these probabilities are normalized, for instance, you know, I mean, if given that, you know, the probability of H0 and probability of H1, they are normalized, so meaning that it's enough that I know a couple of these, like here, this is for the mathematician, you know, and it's enough to know that I know the detection probability and the true positive and true negative, that I can get all the others, okay? For the radar is I want to have the detection and the false alarm. So, but you know, it's a matter of area of application area. And okay. So, if I have one dimension, okay. If I have one dimension, then I can decide, it's like here, you see, I can decide about the decision region R1, the decision region R2, and this is scalar. Okay? And so I can decide that the region is here, and then I can calculate analytically the probability of missing, or the probability of detection, the probability of false alarm. Now, so assuming that I know the probability of X given H0, which means this is the probability density function for X, assuming that the class is H0, then this is the behavior of the probability. And assuming that this one is a probability of x, given that the class was h1. Now, putting the decision region and the threshold of the decision region here, then you know this area, okay? Since this one is the probability of x given h1, now calculating on the region R0, this is the probability that I stay on the region R0 given that it was R1. Okay. And on the other hand, this area is the probability that I stay in R1 given that it was R0. So now you know, since this plus that is normalized to 1 and this plus that is normalized to 1, this is the reason why you know we can it's enough that we get a 2 variable. Now, so this is the probability that I get h0 even if that I have a h1, it's missing. So, and this is the probability, the complementary one is the probability h1 given that the class was h1, the hypothesis was h1. Now, this is this area, how can I sketch? Is the probability, the detection probability. Okay. And the probability that I have h1, even if I was h0, which means the probability that you know I have the hypothesis h1 holds, which means I have a tumor, even if I have no tumor. This is the probability of false alarm. Now, you know, we will see tomorrow, okay, how to design the threshold, how to design the region in such a way that you know the regions are optimal. And then I show you how to make the region, to decide the region, and mostly to design the threshold in case of one variable. We will see tomorrow that in case of a multiple variable, then the regions are strange, or they are separated by hyperplane, depending on the case. Okay, we talked about that.